Hi, in this lecture, I want to talk about a concept in metric spaces, specifically in function spaces, that's called density and how it relates to approximation. Approximation is a powerful idea where you take some concept, some object, such as function, data, shape, image, signal, and you approximate it by something that's easier to analyze. And what I mean by easy will depend on what class you're taking and what applications you're interested in. So these are intentionally quite general, these ideas, but underlying is that we have a collection of objects that we are using to approximate with, and we have some collection of big, sort of more complicated options that are being approximated. So these are approximants, and these play the role of things being approximated. And if we're talking about approximating, we have to have a notion of a distance. So the proper way to talk about this is in the context of a metric space. So we say that a subset D of X is dense if for every X in X and for every distance that we give, epsilon positive, there exists some element, little d, we'll call it A in D, which is an approximant, such that distance from X to A is at most epsilon. So you can approximate X by epsilon at an epsilon distance. So some standard examples of these, which are not particularly interesting, well, every real number can be approximated by a rational number. This is called density of rationals and reals. You could think of it as saying something like every real number can be represented in a computer because numbers in Q can be represented in Q by rational numbers, at least if you allow arbitrary precision. No, real numbers cannot be because you need an infinite decimal expansion, but up to an error of epsilon, you will always find some rational that approximates. So this means that there is a chance that a computer can approximate real numbers. It's kind of a modeling statement. You could think of it that way. So, and what's the proof is that if you fix an X in real numbers, you fix an epsilon positive, then in 131a, there is a theorem that says that there exists a Q in Q such that Q is inside X minus epsilon, X plus epsilon, because this is an interval and every interval contains a rational and balls are intervals. So it's really, again, one of these proofs where you just shuffle the notations. So Q is dense in R. Now, if you take n-dimensional version of this, if you take all the vectors with rational coefficients, then this will be dense in Rn. And the idea is that if you have x1 through xn, then, and you have your epsilon, then you can choose qi such that distance between qi and xi is less than epsilon over n. Now, you change each of the components, xi to qi. This causes, every time you change one of the indices, you have a new error of epsilon over n, but there are at most n indices. So if you do this carefully, you get that the distance between this new point is epsilon. So q to the n is dense in R to the n. Okay, so that's a bit more general. Now there's another way of, we've said about approximating by an element. There's an extreme way of saying this statement, and it's in this spirit of how epsilon delta relate to sequential definitions. And it's actually the exact same proof. I won't recall it now. But if you have a subset that's dense, this holds if and only if for every x in X, there exists a sequence an in D such that limit as n goes to infinity of an is equal to x. In other words, there are equivalent ways of stating this. D closure is equal to all of the space. So equivalent is that D closure is all of x. Every point, every x in x is adherent to D. Both of these are equivalent ways of stating what we just said. So, but the idea in all of these, there are different ways of expressing the idea that you can approximate x up to an arbitrarily small error. And because you can make the error small, so in this proof, if you choose epsilon equals 1 over n, then what you do get, for every n, you get an element an. And you choose such an element, and that gives you a sequence. So you've seen many proofs for this. If you want to practice that, I recommend writing this out, and you can compare your proof to, say, the proof that a epsilon delta continuity is equivalent to sequential continuity. Okay, so now let's see some applications of this kind of idea. And one standard use of density is the following type of lemma. Suppose you have a continuous function on R, and suppose you knew that for every rational number, your function is less than or equal to m. Then you want to show that it's actually less than or equal to m everywhere. And the idea kind of is that, okay, it's a continuous function kind of everywhere in the space. You're less than or equal to m, so after that point, you really have to be everywhere. And this kind of argument, even though itself is sort of doesn't seem like a profoundly interesting statement, is actually quite useful. So let's do this proof and see how the density comes into play. So let's fix f continuous and m as in the statement. And then fix an x in 0, 1. And we want to show that f of x is less than or equal to m. So this is our goal. Let's state it clearly. So how are we going to do that? Well, we were actually going to do, this is a common trick, we're actually not going to show that it's less than m, but we're going to show it's less than m plus epsilon for epsilon arbitrary. And then we send epsilon to 0 at the end. This is a common thing that happens with continuity and sequences and this kind of definitions, because you get the estimate more naturally if you allow a little bit of error. So fix epsilon positive. Now we want to estimate fx from above. So let's look at f of x. And what should we estimate with? We want to estimate it with a rational number, because we know an upper bound for rational numbers, but then we have to add and subtract that rational number's value, so we get fx minus fq. Well, the first one we can estimate by m, but the second one we would like to estimate by epsilon. And when can we do that? When x and q are close. And why? Because f is continuous. So let's do this carefully now. So let's, with the choices. So the question is always, how do we make these? How do we control these? How do we estimate these? So now, since f is continuous, there exists a delta positive such that if distance between x and y is less than or equal to delta, then distance between fx and fy is less than or equal to epsilon. Notice that we have a fixed x, so this is pointwise continuity. So, okay, if the points are close, then we're good. Now, D is equals Q intersected with 0, 1 is dense in 0, 1. So there exists a Q in D such that distance from Q to X, and X is still the fixed value that we have fixed in the beginning, that's less than or equal to delta. But then, for this choice, distance Q to X is less than or equal to delta, Fx is less than Fq is less than Fx minus Fq, and both of these terms we can estimate from above by m and epsilon, respectively. So now let's conclude. So, for all x in 0, 1, we got, for every epsilon positive, Fx less than or equal to m plus epsilon. Now, often how this is concluded is since epsilon is positive is arbitrary, and this is true for all epsilon, then actually Fx is less than or equal to m. And this is what we wanted to show, remember. We wanted to show that specifically. So the way to think about this, I've said it, I think, in a couple of contexts, is you can also say that epsilon goes to 0, because the left-hand side, the crucial thing here is the left-hand side doesn't have an epsilon, the right-hand side has an epsilon. But by sending epsilon to 0, by making it very small, you then have to have Fx less than m. There are other proofs of that too, but that's the basic idea. That's how I usually like to write it. Since epsilon is positive, is arbitrary, then you can remove that from the right-hand side. But it involves this check that it's only on the right-hand side. That's not being said. So that concludes this application, and it gives you a sense of how you can go from information that you have on a dense set to the full space. Often you can translate such an information to the full space. And that ends this section.